Alrighty everybody, so to prove the Riemann hypothesis, first I want to discuss a couple questions which are really the meat and the heart of what is the question asking and what are you trying to prove with the Riemann hypothesis. The title, Proving the Riemann Hypothesis, and we're going to be bounding the determinant. So the first one is the most general. What is a prime number? And this, everyone knows, it's just a number that's only divisible by itself in 1. That's all that needs to be said there. Why do prime numbers decrease in frequency on the natural number line? This is the question Bernard Riemann was trying to answer, I guess, probably, when he formulated his hypothesis. But it's still not the right question. And so the third one I wrote up here is, why do all the non-trivial zeros have real part 1/2? And if you accomplish this right here, this is really what establishes a proof of the Riemann hypothesis. But I wrote these other questions up on the board because they're really the root motivation of what they were asking, or what Riemann was asking. I really don't know the mathematician well or at all. And the word prime, we're going to get to that word here soon. But to prove the Riemann hypothesis, we need to answer this question, and we also need to discuss this question. And the answer to all of those questions is geometry. Sorry, I'm filming this kind of later than the first part because I just do other stuff, but we need to formulate a geometric argument to bound the determinant. And that, we'll get to it right now. So in the first part of this lecture, we asked the question, what was the most general thing a number can represent in a physical sense? And we classified those things. The Big Bang is temperature, then we have the CMB, which is radiation, and then we have stabilization of the CMB into matter. Now we need to ask that same question in a mathematical sense, and we need to ask an additional question, which numbers can create shape? So if you said, what can the number 1 represent? Well, simply just a point. And can you create a line with 1 point? No. So can this create a shape? No. Number 2. We have 2 points, and we have a line segment. 2 points, 1 line segment. Can that create a shape? And shape is a closed object. Shape is closed objects. Closed object. So now we have 2 points and 1 line segment. Is that a closed shape? No. How about the number 3? 3 points, 2 line segments. Can we create a shape? Still no. How about with 4? 4 points, 3 line segments. And the answer is yes. What shape can we make? Well, we can make a triangle. An equilateral triangle. Oh boy. 4 points, right? Now you have to think about this like you're wrapping it around, and we'll get to the physical reason as to why, but I'm just kind of skipping over that right now. So this point, boom, 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 this point would come over here and overlap this one. So this is how you build a coordinate system for those people that really know what's going on. But there's 2 points here. So 3 line segments, 4 points. And now for the rest of them, the answer is all yes. And these are all polygons. You have square, you have pentagon. I can't draw worth a shit yet. But you get the point. Can't draw hexagon with shit. Maybe, yeah. Not going to try to draw an octagon, but that's that. Okay, and now I actually skipped over in the first lecture, pretty bad actually, but I wanted to talk more about the concept of scale. So now we have, this is how we build geometry, and like I said, the polygons represent closed shape. Are shapes. Not only are they shapes, but they're the most basic shapes that can exist. And so now we're going to take this and we're going to model the electron. But the thing I wanted to say about scale is this. The Planck length And I'm using length right now, but this is the Planck scale. They also have Planck time, which is wrong. But it's to the order of magnitude of 10 to the negative 35. And I wanted to touch on how small that is. I want you to think about, I literally want you to try to think about how small you can consider right now. Just think. If you think you're close to 10 to the negative 35, you're way wrong by a whole effing lot. This is literally an imperceptible distance scale. We infer this from measurements. And we'll get to the solving the measurement problem is more broad than solving the Riemann hypothesis, so we're getting there. But this is, my point is this is an imperceptible amount of smallness. And to do that, I wrote up 10 to the 12, right? That's 10 to the negative 35. 10 to the 12 is a trillion. So if you had $1 trillion versus if you had no dollars, that's imperceptible to me. It's probably imperceptible to a lot of people. Not everybody, but a lot of people. So if you put another zero, well, not another zero, but if you made that 20 or 35, that number is literally imperceptible to everybody. And so my point is, when people say quantum mechanics, we don't know stuff, yes, no. I mean, clearly they don't know anything, but nobody understands the concept of, or how imperceptibly small that really is. And that's that. And so now that we've developed a geometric argument, now we're going, and mathematics has to represent real physics, we're going to apply those generalized n polygons to the actual atom. And as a reminder for the physics you need to keep in mind, as temperature decreased, energy stabilized into hydrogen, right? We have the CMB, bunch of energy, temperature, jiggling around, go. Cools down a little bit, then you get electrons, cools down more, then you get atoms. And so now I want you to ask yourself very literally, what is this blob right here? Well, it's a blob of ink, right? I just took a marker and drew a point, right? In mathematics, call it a point. But what is it physically? Well, it's a bunch of atoms, right? You have the ink composed of atoms sticking to a whiteboard of a different structure, also sticking with atoms. And as we established on the other, on the previous video clip, with one point you can't form even a line, and with 2 points and one line you can't form a closed shape. And so the first geometric shape that we have that's a closed shape is a triangle. And this is where this is the ordered pair of why it's real part 1/2. We're not there yet, but this is where the 1/2 comes from, the geometric part of why it's real part 1/2. And we will call these stabilized numbers since they can't form shapes. Stabilized numbers. Actually, we'll just immediately make those sense, and we'll get into this more. But now that I've said this is a blob of ink, well now let's get back to less literal and more mathematics. Let this represent an electron. And I have these little lines here, these are all the same length. And I have written up here on the board, it says the fundamental difference between even and odd numbers is symmetry. Odd number polygons are asymmetric. And so if this is an electron, and this thing's an atom, right? Everything's jiggling around, these are flying around, they're moving. What we know from Newtonian mechanics is that acceleration is inward pointing. I don't know the correct word and I don't want to mess it up. And if you do that on the odd numbered ones, what you see is, if you draw a center point, the distance here from a vertex to the center is longer than the opposing side. So if this is an electron, and like I said, there's not an electron here, but if you had some other mass here, and let's just say there's an electron here, this is exerting more force on the center point than this segment is. Because all of the acceleration vectors are pointing inward. And so the even numbered polygons, that is no longer true, right? This distance is the same distance as this one through the center point. Again, let these represent electrons. And so what you immediately see very easily is any odd numbered polygon is asymmetric. And in a physical sense, This is literally why atoms can vibrate. All right? If this is mass containing, if this is mass, this is going to push more this way than this is going to push that way. So you're going to get, if you could take a snapshot, a momentary snapshot, this is going to be, like the actual atom is going to move this way. And now, an infinitesimal, let's say del t, an infinitesimal amount of time passes. Well, that vertex, which is an electron, is now over here, slightly over this way. And so, over something that isn't del t, the smallest time unit you can do, this thing's actually going to sit here and jiggle, right? And so this is the geometric reason as why atoms can vibrate. So now that we've developed our geometric argument for modeling the electron and subsequently the atom, well, now what I'm going to do is talk about the next most obvious thing, which is the transition of the electron. And this section is really where the conceptual logic makes a ton of sense of the stuff I presented. Namely that energy condenses into mass and mass occupies space, and we're going to see that. Early in the first part of the lecture I talked about something called linguistic heuristics, and I referenced timing is everything, but more specifically what those allow you to do is it allows you to show you the direct transition of a mathematical equation just with simple words that everyone understands. And so the first equation I put up on the board when I introduced the dynamic limit, now we're going to see how that equation is already the equations for energy of a photon and energy for a mass-containing system. And so, to the point of the transition of the electron. All of the atoms around you, all of the things you can see they're interacting with light. So, when an electron's at a higher orbital level and then it jumps down, that's when it releases a photon. And if you're in any accredited school right now today and you said, "Hey, Mr. Professor, what is a photon?" or more generally to quantum field theory, what is a boson? The words out of their mouth is a vibration in a field. And the important physical thing that we take from this is the transition of the electron actually takes some amount of time to happen. So I put brackets around this. And this is demonstrably true right now today. The way we define distance is by literally how fast a photon goes in a given second. So the physical thing that is established as a bona fide fact from experiment, as most foundational thing you can have, is the speed of light. And the electron is not light. The electron is a fermion. It's a spin half particle. More importantly, it has mass. So when this thing jumps, it releases this photon. We don't view, like again, because of Albert Einstein's equation, we don't view energy and mass separately. They're related. And, well, they condense into mass. But after it takes some amount of time for the transition to happen, what we do know is that orbitals are discrete with energy levels n e to the n, where n are integers and E naught is the ground state energy for hydrogen. So what this physical fact gives us a reason for, a direct physical reason for, is we need to make a distinct difference in our counting system, or in our number system, between counting and accounting. And we need to do a lot more physics for that, but for right now, just this is why we can create sets, where I'm going to talk more about it with Fermat's last theorem here in a second, but this is why we can have discrete sets of just one thing, two things, three things, is because of the transition of the electron. And now back to the linguistic heuristics. What I was talking about is, here is the equation for the energy of a photon. E equals the Planck constant times frequency. But for the physical reason that everything's a black body, constants do not exist. So this term becomes the dynamic limit. Energy, we're going to generalize to the word information and subsequently to the word inertia. And this is how we relate the energy of a photon to the energy of a mass-containing system through Einstein's equation. And finally, The nu represents the frequency, and that generalizes to vibration. And so we use the transition of the electron, and that causes a ripple in the energy field that already exists, and we relate that to the mass of the electron. And the way you should intuitively think about that is, where is outer space? Answer that question. Where is outer space? And you probably pointed up there. But up there, you pointed to the edge of the atmosphere. The distance between the marker and the camera or the light fixture, we haven't defined space at all. It's just, we've defined atmosphere. And so it's not really, outer space is not really a difference than the space between right here. And that's how you can kind of intuitively play with the idea that energy actually stabilized into mass, and subsequently we don't really have a good definition of space. And so now we're going to relate this equation to Einstein's equation directly. Now, to relate our equation, like any math equation, we need boundary conditions. And this is where our axioms come back into play. Now that we've developed this equation, this is what proves our axioms correct. What I have here is simply just the E equals a Planck times frequency from last slide, Albert Einstein's equation, and then we'll get to this, but this is the kinetic energy equation from Isaac Newton, or Hooke, or somebody, who knows. But to bound our equation, what we're going to do is we're going to show a time-dependent, unique, I didn't write unique, but unique universal progression. And what we're going to do is, again remember, just walk through and classify energy with these equations. Put zeros in a bracket, does not exist, we cannot measure this. This is not something anyone can measure. And that's why I put a little bracket and big gold question mark. This is the intuitive logic when people say, is there something before the Big Bang? It's not a meaningful question. Stop asking. No one cares. And we have a big blob of energy, which we classify with the property of temperature. Some amount of time passes, which is, again, I don't know. I think it's 10 to the negative 36 seconds. I mean, this is the Planck scale. This is a very fraction of a second. And this is the cosmological microwave background, CMB. And now, what we got to pretty in depth on the last video clip was that photons can be classified by their energy content and their momentum, are the two properties. So, I didn't draw this correctly, but at the time of the CMB, when there was no mass yet, no inertia, there was just photons. So there's just energy and momentum. And now clearly, because all of the things around you have mass, we have atoms, now that energy can be classified by inertia. And the distinct bounds that, the physical bounds that this gives us is, well, temperature, but this is even, okay, I wrote that wrong. 1 second. The temperature at first describes the energy as the property, the correct ontological word that describes the energy content of that time. What the fuck is that? Momentum, then inertia. And so our lower bound is momentum of the, you think of again, mass restricting the movement of light. And that is what inertia is. So absolute zero is the universal lower bound, because every object is sitting there vibrating. We have our little polygon atoms sitting there jiggling around, and everything there's, right, we've all seen there's a billion or a trillion or a whole effing lot. One too many, there's many atoms in that little dot of ink. So many atoms are in the room, I personally have no idea, a whole lot. But everything's interacting constantly, so everything's jiggling around. And then the speed of light is the universal upper bound. And that bound exists because of the CMB, because this is the unique universal progression. And now I want you to notice that I put a two-way arrow here. And this is exactly how we relate Einstein's equation to the energy of a photon, uniquely. One way to do this. And the double-sided arrow represents that once the photon in this atom gets unexcited and flies over there, this process is continuously going on. This is where you get your conservation laws from. This is energy cannot be created nor destroyed, right there. That's what it is. And so the reason I have a box around this equation is you have to keep in mind, again, like I said, science is about 600 years old. That's my estimate. That is an estimate. I don't know. But the point is, Isaac Newton was developing his theory 1, in 1600s, and Albert Einstein developed his in the 1900s, late 1800s, 1900s. So, getting to the title of the entire lecture, where spelling a word constructs a variable, this is really how you see who knows what. And I put a box around this because this is also an equation for energy, but it doesn't have any constants in it. It has mass and it has velocity. And so velocity, now we can understand inertia as, again, how much does something slow down the speed of light? Cool beans. So now to formally relate these equations, all we really need is a very just clear, intuitive picture. The first thing I want to ask yourself is, how fast can something move? And from the last video clip we established, right, there was one point in time, it's the Big Bang. Can't access that anymore. No measurements occurred during that time. Boom. Then we have temperature, or an energy content described by temperature. And then boom, we have the CMB. And I put little like stars here because these are stabilization events. These are when, so this is why, well, I'm going to do another video on strictly on inflation, but it's just not really relevant to this proof. But these are stabilization points that are relevant further on in theory. And then we have atoms, which is our universe. And this is where all measurements have occurred. And again, these are just, I'm just showing the progression. This temperature term right here, I wrote it down because it's part of, these brackets represent the total energy content of the entire universe over time. But this was in the past and no measurements occurred during it. So we're just going to put an X through there. And remember, we have some bracketed del T as temperature cools. And now we have momentum, which is the CMB and just photons. And we have inertia, any particle containing mass. And again, I wrote this as our universe. And I've said it numerous times, but I said this equation, Einstein's equals mc squared, we need to view this as energy stabilizing into mass. And so this is already apparent in, if you're a particle physics student, they'll tell you one field line per one electron. And the reason is because mass and energy are not separate. So I just drew here just a picture. Here's a field line, and here's a constant, here's a vibration in a field, and that's a photon. And then here's a denser field line with more vibrations, which is mass and gives it charge, and now you have your electron. But to bound our entire universe, the movement of any object in the universe, is actually rather simple once we really understand this conceptually. Because this full equation of Albert Einstein, well, now we can take a limit, right? What's the slowest thing? How fast can something move is the upper bound, and how slow can something move is the lower bound. So how slow can something move? Well, if you're a photon, you don't degrade at all. You move at the speed of light always. If you're a mass-containing system, you can't, for the physical reason that everything's an independent black body and constantly interacting with other things, this velocity term can never get to zero. But we can take a limit as it approaches zero. And what happens when we do that? Well, very clearly we have 0 divided by c, 1 minus 0, square root of that is just 1. So we have E equals mc squared. And then we can get rid of this, we can finally get rid of the Lorentz term. And as we know, photons do not have mass. So we can simply relate all of these equations by just writing an ordered pair. That's our lower bound, and our upper bound is c, the speed of light. Oh, excuse me, I wrote that wrong. Any mass-containing system has an energy content, a kinetic energy content, and we'll get to potential energy here in a second, but the kinetic energy content, this is the term that goes there. To be mathematically consistent, I will erase this E. But this now represents the time-dependent energy progression of the entire universe. But not only that, the measurable universe. This is when we have been able to take measurements at any point in time in human history. Wee-hoo. And now we're going to pull that all into the same conceptual framework, and we're going to address the heart of general relativity, which is Einstein's field equation. And to do that, we just need a couple simple statements I want you to keep in mind. Energy is the capacity for movement. Inertia is mass, which is the resistance to change, and rhythm transfers momentum optimally. We're going to address the field equation, and then we will finally solve both the measurement problem of quantum mechanics and the Riemann hypothesis. Oh, one more thing. Once I fix this right here, kinetic energy term is bounded by C. I'll put that right there. And that's for the obvious reason that light can't move slower than the speed of light, and mass can never actually reach the speed of light. And so now, bringing all of these ideas, this is, at the beginning of the lecture I said is we were going to compare the major structures of physics. So we're going to do that now. And to do so, well, first I drew this little, concentric circles. The outer one says physics, then biology, then language, then mathematics. And that should be very intuitive. Everything around you obeys the laws of physics, doesn't it? You're a biological person, right? And biology exists. And now, specific to human biology, we have language, which is broader than mathematics. And so that brings me to the title of the entire lecture, which spelling a word constructs a variable, right? As I've said it before, if you're developing your theory or a theory in 1600s versus 1890, 1900, the amount of known facts is just tremendously different. Now, 200 to 300 years for an individual to say who really knew more about or who was closer to the correct answer of physics, it's really kind of hard to tell, again, besides looking at their equations. But once you spell a word and construct a variable, the context defines it, right? The way you use it in relation to every other word is really what gives it its meaning. And so, bringing the ideas of the last slide into this one, the major thing I want to talk about is Einstein's intuition and how he derived, I don't know, the theory of general relativity. And his intuition was really simple. One day he saw workers working on a rooftop and wondered what it would be like, or what would the workers feel once they fell off. Would they know if they were in a gravitational field or if they were being accelerated? Long story short, he proved that the gravitational mass is equal to the inertial mass. And now from what we've just developed, that directly predicts this, because this is not a distinct equation, right? Mass is inertia. Gravity is a force. So mass has to equal mass because the context defines it. And the context being literally all other physical theory. So that's actually it's a really subtle result, but it's really cool. And now we need to Isaac Newton's mathematics is much more interesting than Einstein's. But looking at the field equation, all this left-hand side of the equation tells you, this tells you the shape of space, the curvature, the Ricci curvature tensor, the gravitational factor, these little mu's and nu's, these are indices for a matrix. And then the infamous cosmological constant, which again, there are no constants. Every object's a black body. This is the mathematical error in Einstein's equation. And on the right side of the equation, we have the stress energy term. And this is matter, this is mass. Shape Matter tells shape how to bend, space tells matter how to move. That's about all Einstein did. And getting back to this little concentric circle diagram, when you're really assessing theoretical structures, you can't take bits and pieces. And this whole equation is the net result of Einstein's understanding of physics, and Newton's equations are the net result of his understanding of physics. The fact that this error exists means he was wrong. And now jumping over to Isaac Newton's equations, these are where it gets more interesting. I said we've successfully completely categorized the time-dependent, the entire evolution of the universe, the energy content. But now, if you remember from any physics, the potential energy is defined as mass times the gravitational constant times height, or displacement, or distance. But as we've been doing this whole time, we cannot have constants. All right? And that gravitational constant is defined as a constant. And so the dynamic limit's a function. So the way you can't directly plug the dynamic limit into Albert Einstein's equation or into any other equation, because you have to, at the upper levels of theory, you are developing an equation. That's what you're doing. So constants don't exist, and this should be viewed as a function. And that's what the dynamic limit is. It's a function, it's a limit. But the reason that Albert Einstein was able to prove that the gravitational mass was equivalent to the inertial mass is because Isaac Newton assumed a wrong mathematical object. The gravitational constant does not exist. There are no constants. That's subsequently how you derive distance, velocity, and acceleration. And so, there's not really much more to say about that, but like I said, it's a really subtle result, but it's really, really cool. And this is, if you said, hey Brad, how do you know that spelling a word constructional error in context defines it over 400 years? It's this result right here. And so now that we've done all of that, we're going to bring all of these ideas into a highly intuitive, very direct framework. And to do that, really what I've done is I've just put a bunch of simple logical steps that everyone can follow, and I'm obviously filming this after a couple days later again, so sorry if I'm trying to pick back up right where I left off. But on the last video clip, the motivation, well, this whole time the motivation for our mathematical equations, we've made the assertion and provided a new mathematical object to model things that are so-called constants but can't be, they have to be functions. And so the last thing that we left off with was the Newtonian equation for potential energy. And as I stated in the title, which is spelling a word constructs a variable, and subsequently that the context that is used defines it, well, we can see how physical theory has gone wrong very quickly. We wouldn't need a bunch of adjectives for different types of energy. We have one thing for energy, we have one thing for work, we have one thing for inertia. So when we start after putting adjectives on our fundamental identities, you've messed something up. And so we need to replace the concept of potential energy with the concept of tension. And from the last slide I said energy is, I think, the capacity for movement. This is the same statement, just more specific. Energy is the capacity to do work. And this is directly, extremely well known since Newtonian mechanics. Work requires movement. Potential is properly modeled as tension. And this should be, let's use the example of going to the gym, right? If you went to the gym right now and you took 10 physical trainers and said, hey man, give me a workout. 9 out of 10 of them will say the term time under tension. And once this is extremely logical. The reason this makes sense is because of the logical framework of defining energy as work. But we're going to model the potential energy, what is called potential energy, as tension. And once we get to the cosmology, that'll be very clear. Inertia is the resistance to change. That's the same thing as the last slide. And now, okay, so where I was going with this is now we're going to take our geometric argument that we've been building, and we're going to show how that becomes a physical argument immediately. So, without any sort of, I drew that little Venn diagram where language is bigger than mathematics. So the identities you can prove strictly with language are broader than what you can prove with equations. And a result from that is simply prime means optimal. Forget mathematics. Someone said, oh, the prime of my life. That's a context which shows you what prime is defined as already outside of mathematics. But now we're going to make that statement a mathematical statement and a physical intuitive realization. What is optimal minimizes waste. No one can deny that. And now what I've pointed out is that rhythm is a fundamental physical principle that has not been integrated properly into physical theory. And rhythm minimizes tension. And this is kind of our end logical statement. And that should be, again, extremely intuitively obvious. If you go to, does dancing release tension? Yes. Does singing release tension? Yes. All of these things require rhythm. That is why. If you're a mathematician or you just like to go on nature walks, this is why. Rhythm minimizes tension. And now, to make that a direct geometric argument, well, we use the thing we just developed, right? These are minimal geometries. You have one point, and now we're going to call these tension points. And these represent where force is exerted the most directly. And then here's a second geometry. We have 2 points and 1 line. Then we have the first shape is at three unique points, and before I was showing you how to develop a coordinate system. But when you wrap that 4th point around here, there's only 3 unique points there. So you need 3 points and 3 lines to create your first closed shape. And this is really the proof. I'm going to say a couple more things, but this right here is the proof of the Riemann hypothesis. You cannot form a closed shape. And now, getting back to going to the gym, now I've been a personal trainer for a while, been exercising for a while. When you have proper form, if you wanted to do a squat, and you put a barbell right on your back, the optimal form is literally going to minimize the contact points between the barbell, your feet, and the floor. So now these points that used to represent the electrons of the atom, now we can generalize that and have it represent any point of contact. This marker hitting my hand, that is a tension point. We have rigorously defined, and I will prove it here in the next couple slides once we get to the measurement problem, why this is absolutely demonstrably correct. But these electrons are not touching. It's a point, not a point particle, but it has electric charge, so it repulses, and it just causes a deformation in my hand. Now, any movement that you do to minimize any sort of external waste, you use rhythm. And this argument, I just drew the first three, but this, okay, well now we're going to take a mathematical limit and show you why this can go to infinity. I gather my thoughts for a second. Okay, really all I'm saying is just, you can put, right, if you drew a square, a pentagon, an octagon, you can maximize the, you can take the limit to infinity of how many tension points there are, how many contact points there are. We'll do that on the next slide. And then now we're going to make the mathematical assertion that a real number must represent a physical measurement. And finally, a zero is a point of intersection. So this next slide, or the next video, will conclude the proof of the Riemann hypothesis, and then the next one we'll conclude the proof of the solution to the measurement problem, and then we'll talk about how all of these things impact current theory in a way that everyone can understand right now. And so finally on the Riemann hypothesis, this is the last kind of thing I wanted to say, and it's really just reviewing basic basic mathematics, but back earlier when I drew the Venn diagram with, or the concentric circles with physics, biology, language, mathematics, once you prove something in mathematics, you can generalize that statement to a logical statement and to keep building theory and proving more identities and whatnot. So up here, what I've written is the interaction statement of vibrational information theory. And this is just the logical statement of the physical progression we've already went through. And that just has mathematical implications. And so, as I said, a number has to represent a real physical measurement. And obviously we have the arrow of time, so there's points in the universal progression that we now have no access to. And we've already gone through that. 0 still does not exist at one point in time. And this, okay, so this is what, earlier I said that we don't need to talk about stabilization events. That was a slip of my mind, that's wrong. We do need to talk about those. What a stabilization event is just the point in time in the universal progression when no measurements had ever came from and they were in the past. So simply again, 0 does not exist. There was a point in time when all the energy content of the entire universe could be classified as temperature, and it is no longer now. And now we have our universe with, I just wrote it as an ordered pair, momentum and then inertia. And that's, I have it written there again. And that's our photons and our atoms. And so now getting to the mathematics of bounding the determinant, when you're given a function like this, right, you're given f of x equals y. You're given some number, you perform some operation on it, and you get back another number. And then on this graph here, I just have the x and the y axis. And so when you're rooting an object, you're finding the center, and that's what I put up there. You're finding an intersection or the center. And to find a root is to center an object. And I said or because again this is back now to strictly the universal minimum. This is a one-time thing. And to do that, or to find a minimum or a maximum, when you set this thing equal to 0, you're condensing the function. And from our geometry or geometric argument, we know this is a minimum geometry. This is the smallest 2 and 1 can ever represent. Two points in one line segment. And on the universal scale, these are the points that represent things in the past. And this is exactly why the Pariah tribe in, I don't even know where, they have a one-too-many counting system. This is literally a tribe of people that have never been exposed to formal mathematics, as far as I know and as far as I can find anywhere in my research. And they only have words for the numbers 1 and 2. And that's again because these things are so, well, not even because they're so far in the past, but because you've never conducted a measurement with completely one or completely two things that describe the entire energy content of the universe. And they cannot, it says 1 and 2 cannot completely represent a physical system. One too many. And so we simply plug this ordered pair in for the coefficients. And all this does is it makes this term right here, it cannot be negative. And you put the 2 in for the B and the 1 in for the A. And you get the minimum bound for the determinant as, and this is, for those, this is the quadratic equation, everyone should know that. But you can't take the square root of a negative number. And this, okay, so I do a bunch of mathematics, and this stuff I've proved, I mean, literally at this point 2.5 years ago. And so there's a lot more mathematical implications from this, and this comes from developing a number system, which I'll get into more detail on different videos, but it's not on this proof. It seems kind of a trivial or arbitrary reason to do so. But the physical reason is there's no negative temperature. And that corresponds to, again, this universal minimum of 1. There is no such thing as a negative temperature. But now, I'm getting to the final title of this final end of the proof. Where is the center of the universe? The astute student says that you can't define it. There is no center, right? I said, where exactly is here and when exactly is now? Apply that question on a universal scale. Where is the center of the universe? There isn't a distinct one because everything is moving, expanding from one another. And so, all of these things are accounted for, all of the zeros of the, oh, let me get there. So if we take our geometric polygons, or n polygons, and we try to find a center, okay, let's say we start right here at this vertex, and now we have to draw a line to not only a non-adjacent vertex, but the opposite vertex. All even polygons, that point occurs right through the center of the closed shape. And this, again, that's our definition of completely symmetric. The complete solution of the Riemann hypothesis has to include even what's called the trivial zeros, and that's at all the negative even numbers, for this exact reason. But now for the non-trivial zeros, when you try to cut one of these objects in half, you always get completely symmetric. Now, dividing the geometric equivalent to 1/2 is dividing by 1/2. And so there's always this point on these odd polygons that it doesn't have an opposite through the center point. It doesn't have another vertex through the opposite. And the proof is really that simple. So that concludes the proof of not only the Riemann hypothesis, and I'll get into why all of these things are already generalized, but prove it's the generalized Riemann hypothesis. But that concludes the proof of the Riemann hypothesis. And now we're going to demonstrate the solution to the measurement problem, which is a lot more poignant. So bringing this entire lectures to a close, we're going to bring all of the ideas together and solve the measurement problem of quantum mechanics. I have up here just a couple simple statements. A mathematical proof, provides direct and incontrovertible evidence of a conclusion. So, you build a mathematical structure, you put a lot of ideas up on the board, you say, look at all these great things, that's what we just did. But now guess what? Nature doesn't give a shit. Nature has to prove you right. The environment, the world around you has to say, this is why you are correct. The second statement I have up here is quantum mechanics does not represent a distinct mathematical domain. So to solve the measurement problem of quantum mechanics, I'm going to prove this statement by direct observation. And so, if you said, what is the measurement problem? It's really what I said before as what exactly causes the quantum wave function to collapse upon measurement. And now I don't even feel like going through the root causes of quantum mechanics, because if you go back and read the physics from 1920, it reads like a cult joke. I mean, just don't even start there. The point is, a collision is a measurement. But to solve the measurement problem, we need to demonstrate evidence of everything I've said so far. And so the third statement I have is fractal scales matters interaction with light. A fractal is a mathematical object that is independent of scale. Its structure looks the same no matter how small or how big it is. This is, again, I really don't know the mathematician well, but this is Mandelbrot, I believe. Marker's running out of ink. 1 second. That one's gone too. And not a subsequent point to this, but just another point. Athleticism is rhythmic motion. We established that to demonstrate that you've built a physical theory, you define something new. No one's defined athleticism before. It is rhythmic motion. But now to prove this, so these are very simple statements. To prove this, all we need to do is have you look at something. I'm not going to draw it up here. I'm just erasing this because, 1 second. A proof of direct observation is quite literally that. Earlier when I said that if you put a bunch of adjectives in front of words, that's how you know you've gone wrong. Now if you go look at the word quantum, go look at where the word quantum is used. It's used everywhere. You can get quantum batteries, you can get quantum slippers, you can get quantum whatever. It's nonsense. To demonstrate all of that simply, there's two things I want you to do. The first one is look at a group of bubbles. Maybe next time you take a leak or you shake up a bottle, look at all of those bubbles that form and look how they interact with one another. When they push up next to each other, they literally form those three-dimensional polygons that we just described. And same with the atom and the electron. On a smallest scale, the electron with its electromagnetic fields. They literally, and you can see this. You can see the tension points. You can literally see that on the bubbles. And the second observation I want you to do is look at the final thing is look at an old computer game representing light and look at a Christmas light in the dark. Again, you will visually see, if you try to sit there and resolve those points, you'll visually see those pentagons. And this is literally when people say they're seeing stars, yeah, you're seeing polygons. And so you might say, how does two things you just wrote up on the board prove the measurement problem? Well, it demonstrates that light does not degrade at any small scale. This being a macroscopic object is made of all of these tiny microscopic objects. If that was a distinctly different thing, there would actually be different laws of physics. There aren't. Period. That's it. Oh, and I guess the final thing I want to say is, like I said, the proof of these problems, this is not even close to the reach of my mathematics. This just establishes the foundations. Now going forward, I'm going to do a bunch of different lecture series on different problems specifically, and building theory in general, and just more broadly into other areas of science. But there you have it.